Hello everyone, welcome to ACE Online. Here ACE Online has started a revision series for the students who are preparing for RRB JE CBT-II. Okay, so we have finished with power systems and now today we will be taking machines. Okay. Right. So, these are the subjects and dates, and every day we will be providing the live session, revision session from 7 o'clock to 8 o'clock in the evening. I just wanted to give you some instruction to the students, those who are preparing for examination. You know it, the examination is on April 22nd. Okay, you can download the call letters 4 days prior to the examination. You just need to go through this website to log in to download the call letter. And you know the number of questions are going to be 150 and marks also going to be 150, but the time duration is of 120 minutes. So, you must be very quick in order to solve this 150 questions. Out of this 150, technical questions are 100 and remaining 50 questions are from general awareness, and you know, these are the subjects from basic computers, environmental and pollution control. Okay. Remember that there is a negative marking. How much negative marking? 1/3. Okay. Right. Please try to gather and you know, let us make the session as interactive. If you have any doubts, you can ask me in the chat box so that I can you know, reply to your questions. Come on guys. Okay, right. So, here we will be discussing about electrical machines, especially in this session I will be taking about transformers and induction machines. Tomorrow's session I will be covering DC machines as well as synchronous machines. Okay. I have taken some you know, some important topics, and along with that I have taken some previous year RRB JE questions also. Okay. So, in this session we will be covering those questions, and like you know, I will explain concept and then we will move on to the questions. So, if you look at the syllabus, this is the syllabus which is mentioned in the RRB JE for the examination. So, single phase, 3-phase transformers, operation, construction, equivalent circuit, voltage regulation, testing, losses, efficiency, and you know, the parallel operation, auto transformers, they have mentioned like this. But if you see majorly from the transformers, if you see the question paper, these are the topics they are focusing mainly. Okay. So, the question is from you know, core construction, maybe from operation and EMF equation, and from testing. So, these are the 3 areas they are focusing more. If you see the previous year questions, you will get to know that, and I will be covering these 3 topics in this session, okay, in the first half of the session. Okay. If anybody is there, please let me know, and let us make the session as you know, interactive. Good evening JE. Okay. We will move on. So, if you see the core, you know, what is the purpose of core? If I have 2 windings like this, or let me take up one winding, and this winding is excited with an AC supply, so that it is going to drive a current. Every current carrying conductor is going to produce a flux, and the flux is trying to establish around the current carrying conductor. The flux always chooses the low reluctance path. Yes or no? Right. So, I have a current carrying conductor I just placed in the air. So, the flux tries to establish around this current carrying conductor. It looks like on the right side as well as on the left side. If you increase the current magnitude, the flux also increases. Okay. So, the flux magnitude or the number of flux lines also going to be increases on both the sides, on the right side as well as left side. Now, if I keep one more winding near to it, if I keep one more winding near to it, now this flux lines will link with this winding and induces an EMF, right. Of course, the same flux lines will link with the own coil and also induces an EMF. We call it as self EMF, and the EMF which is induced in the other coil, we call it as mutual induced EMF. You see, you look at the flux linkages, only half of the flux lines are linking with the second coil, whereas remaining half are not at all linking. This is where the core is useful. How? If you see here, if I put a core like this, let me show you that core. Core is made with a magnetic material, right. So, if I put a core and let me show you the winding here, I am not placing on the core, but just I am showing the winding. Now, whenever you apply a current or whenever you apply an alternating source, it is going to drive the current and it is going to establish the flux lines. Now, the flux lines are trying to establish through this low reluctance path, magnetic path. Earlier some flux lines are establishing on the left side and right side. Now, most of the flux lines will be establishing through the low reluctance path. Because of this low reluctance path, so maximum flux lines are diverted into the core, and therefore, when you place the second winding or other coil on this side, most of the flux lines will be linking with this winding, and hence the induced EMF in this winding will be more. Earlier only few flux linkages, now more flux linkages, and hence EMF is going to be increases. Yes or no? So, the main purpose of core is what? To increase the coupling between the two coils, to carry the flux lines, high amount of flux lines. That is the main intention of the core. Now, if you are expecting more flux lines passage or more flux lines establishment through the core, how it should be designed is a question. How it should be designed is a question. So, if you see this core, this is how I can show you the flux direction. How it should be designed? It must be a magnetic material, no doubt. How this magnetic material should be designed? It should have low reluctance, it should have high permeability, and along with that it should have low hysteresis coefficient. So, these are the three main features for a core. Core should possess these three main features. If the core is going to possess low reluctance and high permeability, definitely the flux can easily establish through the core. And if the hysteresis coefficient of this magnetic path is very low, the hysteresis losses will be very low. That is the main intention behind the core. Okay. There is one more thing also. While the flux is establishing through the core, no material is 100% perfect. Yes or no? No material is 100% perfect. It has some impurities. So, what I am trying to say is, this is not exactly 100% magnetic material. It will possess some conducting properties also. What are the conducting properties? How can you represent the conducting properties? With the free electrons. Yes or no? So, here and there I can represent free electrons. So, when an alternating flux is establishing through the core, those flux lines will definitely interact or create some force on these free electrons. That force we call it as EMF. As the EMF is created on this electron, EMF is nothing but what? Electromotive force. A force is creating on the electron because of these flux linkages, right. This EMF is not induced in the winding, it is induced in the core. It is useless actually, we do not want that. In the core, only flux establishment should be there, na? EMF should not be induced. If EMF is induced, that force is going to drive the electrons from one place to another place, and it results in eddy currents. Now, the flow of these electrons results in eddy currents, and because of the current flow or because of those electrons flow, you will get a collision and hence heat dissipation. So, we call it as eddy current losses. Yes or no? Okay. I hope it is clear. In order to minimize these eddy current losses, we will be going for laminated steel. That means, do not use a solid core, use a piecewise structure, thin laminations. The area of cross section of the core should be very, very small laminations, and you can bring them together to form a core. The process of bringing the laminations together, you can call it as core staggering. Okay. You know, remember, while bringing all the laminations, this is one sheet. Now, if you want to place one more sheet, between the two sheets there must be an insulation. Okay. Maybe a painting or paper you can place. Okay. Right. So, that means what? If you look at the core, magnetic material is there, insulating material is there, not 100% core material, not 100% magnetic material, some amount of iron material and some amount of insulating material. Remember this point. Okay. So, why are we doing this laminations? To reduce the eddy current losses. How can you do that? You know, if you see laminations, we know resistance is inversely proportional to area of cross section. If you reduce the area of cross section, the resistance is going to be increases, which means whatever the electrons which are existed in this sheet will experience a high resistance because of small laminations, because of thin laminations. If the resistance is more, current strength will decrease and hence eddy current loss also decreases. So, that is the main intention behind the thin laminations, and because of the laminations we will be using insulating material. So, because of that you will get one more factor, that is called iron factor or stacking factor. Okay. Right. So, this is a small information about the core. I hope it is clear. Please try to respond so that we can make the session interactive. Okay. I hope it is clear. Let us have a look at some questions on the core. I have a question like this. A transformer core is made up of laminations. Option A, to increase the electrical conductivity of the core, to increase the permeability of the core, to reduce the eddy currents, to increase eddy currents and improve efficiency. Will you increase the eddy currents? No, right? This is absolutely wrong. Is it to increase the electrical conductivity? No. Is it to increase the permeability of the core? No. So, laminations, because of laminations, area of cross section of the sheet can be minimized or core can be minimized, so that you can minimize the current flow, that is eddy current flow. Yes or no? So, C is the correct answer. Very good, Balaji, JE and Chakrit Reddy. So, let us have a look at another question. Look at this one. The value of stacking factor is usually equal to unity, greater than unity, 0, less than unity. Stacking factor is also called as what? Iron factor. So, generally we represent with Ki or Ks. So, the name itself is saying that iron factor, which means in the core how much amount of magnetic material is there and how much amount of non-magnetic material is there. So, as I said, we have laminated core, and between each and every lamination we have insulation also, insulating material also. So, the core is not 100% magnetic material, it is less than 100%. So, the stacking factor is defined as ratio of net area of cross section to the gross area of cross section. What is net area of cross section? It is the area occupied by magnetic material. Area occupied by magnetic material. Gross area of cross section area occupied by magnetic material gross na plus area occupied by insulating material or dielectric material. So, if you see the core, you have magnetic material and insulating material. Together it is 100%. So, the denominator is going to be 100%. If you see the numerator, area occupied by magnetic material only, na? If you see the numerator, area occupied by magnetic material only, it is less than 100%, na? So, generally it is going to be around 90 to 95%. So, I can say 90 by 100, you will get it as 0.9. So, 90%, 0.9, or otherwise I can write 90%. Okay. So, less than unity only, less than unity could be the possible answer. It cannot be greater than unity, it cannot be equal to unity also, it cannot be 0 also. So, the only option is less than unity. Yes or no? Very good, Sayali, right, JE and Shivachakrit Reddy, right. Let us see one more thing, one more topic, that is operation of transformer. Okay. So, if you look at the transformer, it has major parts are core and winding. You can call this winding as, if number of turns are more, you can call it as high voltage winding, and I am calling this as high voltage winding, and I am writing or indicating a name as N1. If the winding has less number of turns, you can call it as low voltage winding, and I am numbering it as or designating it as N2. Okay. Basically, the windings are high voltage winding and low voltage winding. Do not call them as like primary winding and secondary winding, because you can give the supply on this side, otherwise you can give the supply on this side. If you give the supply here and you have to take the load here, or you have to connect the load here, so that this becomes primary and this becomes secondary. If you connect the source here, this becomes primary and you have to take the load here, so it becomes secondary. Any winding can be taken as primary or secondary. Remember that point. So, basically you should call them as high voltage winding and low voltage winding. If the number of turns are more, high voltage winding; if the number of turns are less, low voltage winding. Okay, right. If single phase transformer, for 3-phase transformer you will be having 3 windings on the primary side as well as secondary side. Okay. So, let us get into the operation. So, I have a current carrying conductor, connect an alternating source. So, this voltage source V of t, whenever you connect an alternating source, it is going to drive a current I, right. Generally, if it is on no load, so the current drawn by the transformer is going to be no load current. It has 2 components, magnetizing component of current and working component of current. Magnetizing component of current is going to set up the flux. Okay. So, when the flux is going to be established in the core, the flux links with this winding. As it is an alternating winding, there will be variations with respect to this winding, and hence an EMF is going to be induced in this winding. I am calling it as E1. An EMF is also going to be induced in this winding. I am calling it as E2. Okay. The flux produced by this number of turns, no, because we are giving the supply to this turns. So, these flux lines are, we can call this as self flux lines. So, if own coil flux lines are linking with its own coil, then the EMF is called as self induced EMF. Okay. Now, with respect to this coil, other coil flux lines are linking with this coil, so you can call it as mutually induced EMF. Okay. Mutually induced EMF, right. So, if you see, now EMFs are going to be induced, right. Now, main function of transformer is what? To transfer the power from one side to another side. Okay. So, I have connected a load here So, I have connected a source here, now I have to connect a load. So, if you connect a inductive load or capacitive load, generally majorly it is going to be inductive load, most of the loads are going to be inductive load. I have connected a load. So, I have closed the circuit here. So, whenever the circuit is closed, we have a potential here or potential difference you can find. Now, this induced EMF is going to circulate a current on through the load. So, whenever current is going to be set up, now this current carrying conductor will also create a flux. In which direction? This current carrying conductor or this low voltage winding will set up a flux in opposite to very cause for the production of induced EMF to satisfy or to obey the Lenz's law. Yes or no? So, this EMF is going to drive a current and is going to set up a flux line in opposite to this flux line. Okay, we call it as phi 2. Now, because of these interactions, there might be chance of decrement in flux in the core, and due to which EMF can reduce, and because of the reduction in EMF, the potential difference between winding and winding EMF and source will increase, and that is the reason why when extra current will be driven into the winding, we call it as I1 dash. Earlier I naught, now I1 dash. Now, I1 dash is going to create one more flux, that is called phi 1. Now, phi 1, why phi 1? What is the purpose of phi 1? So, phi 1 is because of I1 dash. I1 is because of what? Because of increase in potential difference. Why the potential difference is increased? EMF is decreased. Why it is happening? Phi 2 is opposing the phi. So, to satisfy the Lenz's law, this I1 is creating a flux phi 1, and this phi 1 is going to oppose the phi 2. So, now phi 1 and phi 2 will be compensated, and at the end of the only phi m is available in the core. Yes or no? Only phi m is going to be available in the core. The same way, even you increase the load also. If you increase the load, current increases. If current increases, flux increases. If flux increases, opposition increases. Potential difference increases. If the potential difference increases, current increases. If the current increases, this phi 1 also increases, and again this will be compensated. For every load, this goes on. End of the day, the flux available in the core is going to be phi m only. Whether it is under no load or half load, 25% load, full load, any load for that matter, the flux in the core is going to be constant. What is that flux? Phi m. Constant does not mean that time invariant. It is a time varying flux only. Constant means from no load to any load. Okay. That is why we call the transformer as constant flux device. Yes or no? Constant means constant from no load to any load. Constant does not mean that time invariant, it is time varying only. Constant means from no load to any load. Okay. So, if you see the operation, what you can understand here, the power is transferred to the load side by means of one principle. What is that principle? Electromagnetic mutual induction. This load is driven because of E2. E2 is what? Mutually induced EMF, mutual induction. Okay, mutually induced EMF. So, that is the reason why the principle of operation of transformer is mutual induction. Okay. So, operating principle is mutual induction. So, principle and this one is very important, constant flux device. Okay. Right. Now, we will see some EMF equation and then we will conclude some points. If you look at EMF equation, E is proportional to rate of change of flux linkages. So, based on this equation, we will be getting, if you solve small e or capital E anything, if you will be getting EMF is equals to 4.44 into N into phi m into F. So, this is much generalized EMF equation of a transformer. Okay. We have two windings, high voltage winding and low voltage winding. I made it as N1 and N2. Okay, generally, so I can write here E1 is equals to 4.44 into N1 into phi m into F. Okay. Or otherwise, I can also write on the secondary side E2 is equals to 4.44 into N2 into phi m into F. Right. So, in general, I can write this equation, as E divided by N is equals to 4.44 into phi m into F. So, what does it mean? EMF per turn is going to be equal on both the sides. You take up E1 by N1, you take up E2 by N2. E1 by N1, E2 by N2 will be equal. So, E1 by N1 is equal to E2 by N2. So, how much is that? 4.44 into F into phi m. Remember, this phi m is nothing but maximum value of flux. Maximum value of flux. Actually, this psi na flux linkages. Flux linkages we will representing it as N into phi. What is this phi? Time varying flux, phi of t. So, phi of t we will be writing it as phi m into sin omega t na. Phi of t we will be writing it as phi m into sin omega t. This is a maximum value, not mutual flux. Remember, there is a maximum value, not mutual flux. Okay. So, remember this point, it is very, very important. EMF per turn on both the sides of the transformer windings is equal. And you see here, when the flux lines are establishing in the winding or in the core, when the flux lines are establishing in the core, they are linking with the winding. Whatever the rate of change of flux linkages at this winding, the same rate of change of flux linkages will be there at this winding also. The rate of change of flux linkages on both the sides will be same. Therefore, the rate at which the EMF induction is also same. That is what I mean to say is, the frequency of induced EMF on this side, on both the sides will be same. It's just like this, you treat my face as core. Okay. So, these are my flux lines. Flux lines variation on the primary side and secondary side will be same. Okay. So, whenever the flux lines variations are going to be same, the rate at which the EMF induction is also going to be same. So, the frequency of induction is going to be same. What I mean to say is, you just slap with the two hands on your face, the pain you are going to get or the intensity of pain you are going to get on your two cheeks will be same. Because whatever the rate of change is there on the left side and right side, it will be same. That is why we call transformer is a constant frequency device. Transformer is a constant frequency device. Okay. Right. One more point I wanted to add up here. Whatever the magnetomotive force produced is going to be compensated by this magnetomotive force. Phi 2 is going to be compensated by phi 1 na. So, here the magnetomotive force produced on the secondary side, the magnetomotive force produced on the primary side will be same. So, we write it as N1 into phi 1, or let me write N1 into I1 N1 into I1. You can write MMF is equals to flux divided by reluctance. So, I am not just writing, I am writing in this manner. N1 into I1 is equals to N2 into I2. Okay. We have got one thing, that is EMF per turn on both the sides is same. I can rewrite this as E1 by E2 is equals to N1 by N2 or not, or other way E2 by E1 is equals to N2 by N1 or not. Okay. So, I have got here N2, N1 and N2. So, I can replace this as E1, I1, E2, I2. I am replacing N1 with E1, I am replacing N2 with E2, because I have got EMF per turn on both the sides as same. Okay. So, if you look at this equation, I can say voltage into current, it is a power, voltage into current, it is a power. The power received on the primary side, the power received on the secondary side is equal, which means transformer is a constant power device. So, I can say here transformer is a constant power device. Remember, it is not active power, it is not reactive power, it is actually apparent power device. Transformer is a constant apparent power device, not active power, because do you have cos phi? No. Do you have sin phi? No. V into I, it is just volt ampere only, not kilowatt or not watts or otherwise VAR. Transformer is a constant apparent power device, not an active power device, not a constant active power device, not a constant reactive power device, remember. Okay. So, I wanted to put once again, I wanted to repeat the points again. Transformer is a constant flux device, transformer is a constant power device, transformer is a constant frequency device, and it operates based on mutual induction. Okay. So, if we have seen the EMF equation and we have got one conclusion that EMF per turn on both the sides is of same. Remember that point, phi m is maximum value of the flux. Okay. You know, you can call this ratio, especially this one, you can call this ratio as transformation ratio. E2 by E1 is equals to N2 by N1, you can call it as transformation ratio. K, we generally represent with K. Okay. Right. I am not mentioning here low voltage winding, high voltage winding, it can be anything. You can use the transformer as step up transformer, step down transformer, it is okay. In general, I am representing. If you write in terms of N1 by N2, it is a turns ratio, remember that. So, this is going to be a turns ratio. Be careful with the turns ratio and transformation ratio. Okay. Remember, and I wanted to add up one more point here, as we have got 4.44 into F into phi m into N, I am writing this maximum flux as maximum flux density into area of cross section, generally net area of cross section. Okay, because flux density is equal to flux per area, na? So I am writing like this. Rest all other going to be same. Okay, F and this constant symbol. Now I can write here EMF is depending upon frequency, EMF is depending upon flux density. I can rewrite this equation as the maximum flux density is directly proportional to EMF and inversely proportional to F. EMF depends on what? EMF is proportional to voltage applied. So I can rewrite this equation as voltage and divided by frequency. This is very, very important. This is very, very important. So they will ask you like transformer is operated on rated voltage, but not at rated frequency. If the frequency is reduced, what happens to the flux density? So these are very important. The points which I am putting in the box are very, very important. I am trying to cover only few points. They are very, very important. Okay. I hope it is clear. If you have any doubt, you can ask me. Right. Remember, this is net area of cross section, not gross area of cross section, because only iron content we will be taking, because flux establishes only through the iron content or magnetic path content, not through the insulating material. So do not take up gross area of cross section. So let us have a look at some questions here. The value of flux involved in the EMF equation of transformer. Is it instantaneous flux or maximum flux or average flux or RMS value of flux? What is that flux? Can you tell me? Instantaneous or maximum or average or RMS? Come on, my dear. Maximum value or not? Just now we have seen EMF equation E is equals to 4.44 into F into phi m into N. So, this one maximum value or not? Very good, Chakrit Reddy. Come on, let us take up one more question. If you look at this question, the frequency of the secondary voltage of a transformer will be less than the frequency of primary voltage, equal to the primary voltage, greater than the frequency of primary voltage, very much greater than the frequency of the primary voltage. We have seen EMF per turn is same. You see the EMF equation, whether the EMF induced on the primary side or on the secondary side, the frequency of induced EMF is same or not, whether on the primary side or secondary side, or high voltage side or low voltage side, does not matter, right. Frequency, transformer is a constant frequency device, na? Constant frequency device. So, I can say that equal to the primary voltage. Yes or no? Now, let us have a look at this question. The ratio of secondary turns to primary turns in a transformer is 3. He has given a ratio of secondary turns to primary turns. Be careful, N2 by N1 he has given. Now, he is asking if the EMF in the secondary coil is 600, the EMF in the primary will be, he is asking. EMF in the secondary coil I am writing it as E2, the EMF in the primary coil it will be E1. Secondary coil he has mentioned that is 600, he is asking for primary coil EMF. So, we know the EMF equation, right. EMF per turn also we have seen, right. EMF per turn E1 by N1 is equals to E2 by N2. He is asking E1. So, E1 is equals to what now? E2 by N2 into N1. What is E2? He has mentioned it as 600 or not? What is N2? Did he mention any number of turns on the secondary side? No, he did not mention, but he mentioned N2 by N1 as 3. N2 by N1 as 3, N1 by N2 will be 1 by 3, na? So, I can write this as 1 by 3. So, you will get it as this N2 by N1 will be 1 by 3. So, you will be getting it as how much? 200 volts. So, C could be the correct answer. Okay. You just look at the question. Okay. Here N2 is 3, N1 is 1, which means N2 is greater than N1 or not? N2 is greater than N1 is nothing but it is high voltage winding and it is low voltage winding. So, definitely E2 will be greater than E1 or not? Yes or no? If N2 is greater than N1, if more number of turns are there on the secondary side, it is like a step up transformer. Okay. This is like a step up transformer or not? So, definitely E2 will be greater than E1. E2 is how much? 600, which means what? E1 must be less than 600, na? 1800, 900, 600. So, out of these 4 options, I can eliminate 3 options. So, the only answer is going to be 200. So, you can eliminate options and you can find out the answer also, if you do not get this calculation. Okay. Right, Sayali, very good. JE, okay. Let us have a look at one more question. A step up transformer increases. Will it increase power? Will it increase resistance? Will it increase voltage? Will it increase frequency? Transformer is a constant frequency device, na? Transformer is a constant apparent power device, na? Okay. So, generally transformer is useful to increase or decrease the voltage levels and currents. So, option C could be the correct answer. Yes or no? Right. Generally resistance is based on the number of turns you can have. High voltage winding, coming to the resistance, let me tell you some points here. High voltage winding will carry less current. Low voltage winding will carry high current. Remember this point. Okay. You know why? Let me make this as N1 I1 is equals to N2 I2. N1 I am writing it as high voltage winding, N2 I am writing it as low voltage winding. If number of turns are more, current must be a lesser value so that this product will be same, constant, because number of turns are less here. To get this amount, this product, or to get equal to this N1 I1, I2 must be greater, na? Must be higher value, na? So low voltage winding will carry higher current, high voltage winding will carry lesser current to have equal amount of magnetomotive force in both the windings. They should be equal and opposite. Then only the transformer will be a stationary device. It won't move because fluxes can be compensated, can be cancelled, and it won't move. The transformer is a stationary device, it is not going to be a rotating device. If high voltage winding is carrying less current, which means what? High resistance, na? The winding, high voltage winding resistance is going to be high. Low voltage winding is going to carry high current, which means what? Resistance is going to be low, na? So high resistance and low resistance for low voltage winding. Okay. So sometimes I'll ask you, if resistance is high, how it should be designed? Length by area. If resistance is high, length of the winding is high and area of cross section is less, which means high voltage winding is of long length and thin cross section or thin area of cross section. Low voltage winding, less number of turns or lesser length and thick cross section, so that your resistance of the winding will be less and it can accept more currents. Yes or no? So these points are also very important. Let us have a look at one more question. A transformer has 1000 primary turns. It is connected to 250 volts AC supply. Find the number of secondary turns to get secondary voltage of 400 volts. Find the number of secondary turns is asking, N2. So you know the equation, E2 by E1 is equals to N2 by N1. He has given it has a primary turns of 1000 and it is connected to 250 volts voltage source. E1 is going to be 250, right? He has given, he is asking find the number of turns to get a secondary voltage of 400. So E2 I am writing it as 400. So you just multiply, you will get N2 value. How much it will be? 400 into 1000 divided by 250. 5 5s, 5 2s, 5 4s. So approximately you will be getting 1600 turns. Yes or no? So your answer is going to be A. Very good. Very good, JE and Balaji. Now let us have a look at this question. When a given transformer is operating at its rated voltage with reduced frequency, its iron losses are reduced, flux density remains unaffected, core flux density is increased, core flux density is reduced. Voltage is rated, frequency is reduced. We have seen, na? The maximum flux density is proportional to what? Voltage and frequency. Voltage, he is maintaining rated voltage only. He is not disturbing the voltage, but he is reducing frequency. If the frequency reduces, the maximum flux density establishment in the core will increase. Okay, right. If the flux density increases, what happens to iron losses? There will be definitely change, but you know, you can change, you can expect increment only, but he has given reduction. Flux density remains unaffected. Is it unaffected? No. Flux density is increased. So C is the correct answer. It is not decreased. Yes or no? Okay. Now look at this one. Transformer rating are usually expressed in, will it be expressed in kVA, kilowatt, kilowatt hours, kVAR? Okay. We have seen one formula, E1 I1 is equals to E2 I2, power equation na, apparent power, volts, E1 units are volts, I1 or current units are amperes. So it is volt amperes kVA, but not kilowatts or kVAR. Okay. So transformer ratings are expressed in generally kVA. There is a reason, like major parts are core and windings. Core losses or hysteresis loss and eddy current losses, they depend upon flux. Flux depends upon voltage. So iron losses depends upon voltage, and copper losses, the heat losses which are created in the winding, that depends upon current. So current is going to create copper loss, voltage is going to create, of course, iron losses. So iron losses depends upon your voltage and copper losses depends upon your current. So on the whole, what I am trying to say is these losses are going to create heat. These losses are going to create heat. For designing any device, for designing any electrical device or any electrical machine, temperature is a main constraint. Remember this point, because if lot of amount of heat is developed, it cannot operate smoothly. It cannot perform the its work smoothly. Temperature is a main constraint for any device, for any mechanical device or electromechanical device. So the temperature production is depending upon what? Voltage and current. That's the reason why generally we write it as on, we put the units in terms of kVA. And one more parameter is also there, one more point is also there, that is power factor will not influence these losses. And do not fix the power factor at all. Do not fix the power factor, because you can place any amount of load on the transformer. The loads are going to be changes. If it is a distribution transformer, the loads in the morning, the loads in the afternoon and evening will be changes. If the load changes, load power factor also changes, na. So if you fix a kilowatt, that means what? Voltage into current into power factor. If you fix this power factor, kilowatt rating will be fixed. That means what? Power factor you are fixing. If you are fixing the power factor, you cannot have variable loads operation. Operation is going to be unsatisfactory operation, because you are going to design the transformer maybe at 0.8 or 0.6 or 0.9, but the load power factor is going to be changes time to time. This power factor is not able to match with this power factor, so unsatisfactory operation may take place. So to avoid all these things, it's better to go ahead with the kVA. Synchronous machines rating will be on kilowatts, remember that point, because on the synchronous generator the load is going to be constant, load is not going to be changes, load will not change with respect to time, it is going to be constant. Synchronous machine generators, I am saying about synchronous generators, power plant generators, the rating is in terms of kilowatts, because power factor is predetermined. Full load power factor 0.8 or 0.9 they will decide, and you can even control with excitation also. So that is the reason why we generally define synchronous generators rating in terms of kilowatts. Okay. Now look at this question. What kVA rating is required for a transformer that must handle a maximum load of 8 amperes with a secondary voltage of 2 kilovolts? Load current he has given, secondary voltage also he has given, E2 and I2. So what is the load kVA it can handle? kVA E2 into I2, how much you will get? 2 kV into 8 amperes. So you will get 16 kVA. C is right, na? Okay. So those are some questions on operation, and coming to the testing, we will see testing. Majorly the parts are, transformer parts are core and windings. Yes or no? If you want to test the core, if you want to test the core, you will be conducting open circuit test. How to test this? Core purpose is to carry the flux lines. So you have to test the core at rated flux lines. Okay. How will you get these flux lines? If you want to get these flux lines, B maximum is proportional to V by F na. So you have to apply rated voltage and rated frequency. Remember this point. If you want to test the core, that means what? Open circuit test only. Core test is also called as open circuit test. You must apply rated voltage and rated frequency. Therefore, so that the flux establishment in the core will be rated value. Okay. So that you can find out hysteresis and eddy current losses. Hysteresis loss are proportional to B maximum power X into F into V, and eddy current loss are proportional to B maximum square into frequency square into thickness of lamination square. Okay. So the main aim of the core test or otherwise open circuit test to find out these losses, iron losses or core losses. We are testing the core whether it is carrying rated flux or not. While it is carrying rated flux, some losses are happening, and these are the losses, hysteresis and eddy current losses. Okay. Now coming to winding, I wanted to test the winding whether it is carrying rated current or not. Winding purpose is what? To carry the rated current. Okay. Now to circulate rated current, we generally we have to put rated load. On the secondary side, we have to put rated load. But to create rated load, unnecessarily, it's a useless or unnecessarily it's a wastage of power. If you create a rated load, unnecessarily you will be wasting some amount of power. So we don't create a rated load, we create a short circuit, imaginary rated load, that is called. Okay. So to get a rated current circulation, what we do is we apply less than the rated voltage, that is short circuit voltage, less than the rated voltage. VSC is less than the rated voltage. It's hardly 10% of rated voltage only. It's hardly 10% of rated voltage is enough. To find the core losses, rated voltage, rated frequency must be there. But to find the winding losses, we will be applying less than the rated voltage. Remember this point. And frequency is going to be rated, remember. Frequency is going to be rated. Okay. Right. So winding, because of circulation of current, you can find out heat, and the winding, what I can write, copper losses. So the winding test is also called as short circuit test. Core test is also called as open circuit test. In open circuit test, you will find out iron losses. We also call this as constant losses. And in winding test or short circuit test, we will find copper losses. We also call it as variable losses. Okay, right. So these are some important points about testing. Let us have a look at this question. Open circuit test in transformer is conducted to determine core test. Open circuit test is nothing but core test. In core, you will get two losses, hysteresis and eddy current losses. So he is asking, is conducted to determine what? Hysteresis losses, copper losses, core losses, eddy current losses. Both we will find. So both are together is nothing but what? Core losses or not? So C is the correct answer. Don't go with A or D, C is the correct answer. Now if you look at this one, short circuit test on transformer is also known as winding test. But do you have winding test? Capacitance test, impedance test, inductance test, current test. Okay, we are not testing the current, remember, we are driving rated current. Okay, we are testing the winding whether it is carrying rated current or not. While rated current is flowing, copper losses are taking place. Okay. So short circuit test is also called as winding test. What winding will be having? Generally the winding is represented as what? Winding test. Winding is represented as what? In electrical terminology, winding can be represented with resistance and reactance. Okay. So together you can call it as impedance. together, you can call it as impedance. So, that is why this test is also called as impedance test, because winding parameters you will find out right at end of the day. Look at this question. The losses in a transformer are copper losses, eddy current losses, hysteresis losses. The constant power loss of a transformer is given by 1 only, 2 only, 3 only, 2 and 3 only. He is asking constant losses. Okay. Why are we calling them as constant losses? Because generally we will apply rated voltage constant, that is constant. We generally do not change. If you do not change, here voltage is constant. If voltage is constant, voltage and frequencies are going to be constant, flux is constant. If flux is constant, the associated loss, hysteresis loss and eddy current loss also going to be constant. Yes or no? We are making frequency as constant, voltage as constant. So, flux density is constant and hence the associated loss is also going to be constant. You know, how can you make this as constant? You apply rated voltage and rated frequency. That means what? Even though you change the load, there will not be much change in EMF. There will not be much change in the flux. From no load to any load, the flux in the transformer is going to be constant. So, therefore, the associated losses in the core also going to be constant. Whereas, in winding, if the load changes, current changes. If the current changes, copper losses also changes. That is the reason why copper loss are called as variable losses. Okay. Copper loss is a variable loss, whereas these two are constant loss. It is, you are defining actually with respect to load. If there is a load variation, current varies. If the current varies, copper losses varies. But is there any change in the flux in the core? No. From no load to any load, the flux is same. That is the reason why the transformer core losses are going to be constant. So, 2 and 3 could be the correct answer. Okay. Right. Now, if you look at next question, which part of the transformer is subjected to maximum heating? Maximum heating, where do you get? Wherever there is a current flow or huge amount of current flow, you will get huge amount of heat. Do you expect a current flow in the frame? No. Do you expect a current flow in the core? In the core, flux has to establish. A minor current will flow, that is, eddy currents, and due to that you do not get much heat. So, you will get a heat from the core, but you do not get much heat. Oil, will it circulate? Will it accept current? No. Oil will absorb the heat. Okay. So, winding is going to carry the current because it carries the current, it carries the main supply current. So, you get more amount of heat in the winding. So, maximum heat producing part is what? Winding. Now, we look at efficiency. So, there is one more important point, one more important area where you can expect a question, very repeated and frequently asked question. Efficiency, you know the formula, ratio of output to input. Okay. Generally, we also write this as output by output plus losses also. Putting all these things, and if you derive, they will ask you condition for maximum efficiency. When will you get maximum efficiency? So, the answer is what? Copper losses must be equals to iron losses. This is the condition where you will get maximum efficiency. Copper losses has to vary and it has to become equals to iron losses, then you will get maximum efficiency. We will also write, remember this is not a full load copper loss, not full load copper loss. Remember this point. Remember, copper loss should vary because it is a variable loss, and it must be equals to iron loss. Iron loss is not a variable loss, it is a constant loss. So, on the whole, at maximum efficiency, the total losses will be what? Copper losses plus iron losses. So, at maximum efficiency copper loss is becoming equal to iron losses. So, iron losses plus iron losses, I can write it as 2 times iron losses. At maximum efficiency, the total loss must be equals to 2 times iron losses, but not equals to 2 times copper losses. Remember that point. Total loss is not equals to 2 times copper losses, because copper loss is changing and becoming equal to iron loss. Remember that point. This is very, very important. Condition is also very, very important. We also write it as variable losses equals to constant losses. Okay? Look at this one. A transformer is working at its maximum efficiency. Its iron loss is 1 kilowatt. Its copper loss will be how much? He has given maximum efficiency and iron loss also. Copper loss is asking. Just now we have seen at maximum efficiency, copper losses are becoming equals to iron losses or not? Iron losses he has mentioned it as 1 kilowatt. Now how much is the copper loss? 1 kilowatt only, na? Yes or no? So these are some questions I think on transformer. So if you look at the transformer, you see conservator, some lightning arresters and bushings. These are lightning arresters to save the transformer. These are bushings. Conservator, we can have fan for cooling, and we have windings inside. So this is a beautiful construction of a transformer. Now we will see induction machines. So this is the syllabus of induction machine. They have given right from operation, construction, torque, speed characteristics, starting methods, okay, even including braking and single phase induction machines also they have mentioned. But I have seen the previous question papers, mostly the questions on operation of induction machine, operation of induction machine, operation of induction motor, most of the questions. Whether it is a transformer or induction machine, you see any machines questions, basic concept oriented questions only. Okay. And if you see the weightage, I forgot to tell you the weightage also. The weightage is going to be around 4 to 5 questions. Transformers 4 to 5 questions, induction machines also 4 to 5 questions, DC machines and synchronous machines together it will be touching to around 12-13 questions, around 11 to 13 questions. So altogether it will be minimum of, I can say minimum of 18 questions, and maximum it can go up to 22 questions. Okay. 4 4 is 16 or 4 5 is 20, like that it will be 4 minimum, and maximum it can touch 6 7 also, especially in synchronous machine 6 questions, 7 questions, 8 questions also they have asked. Okay. Synchronous machine has high weightage, of course even DC machines also little bit here and there. Okay. Right. So let us have a look at operation of induction motor. We will quickly complete. So let me show you some figures related to induction machine. You know, if you see, it's a stator. It's a stator. He has given starter terminals. They have given starter box. Stator, this one, and rotor. And you know, anyhow, this is a shaft, and you have closed wing, closed couplers, or you can call it as outer frame, and you can find a fan here to dissipate the heat or to circulate the cool air inside the machine, into the machine. And this is, if you see the open view, we have a cylindrical structure of stator and cylindrical structure of rotor like this. Of course, shaft, and we have slip ring also, or sorry, that is a bearing. These are laminated stator slots, the stator core, and we have a slots here, semi open type slots. You can see I did not have a cross sectional view or a side view, that is a one side view, or a front view, you can say top view. This is how the squirrel cage rotor looks like. You can have insulated laminated sheets. You can bring them together, and it looks like a squirrel cage rotor. cylindrical body. The slots are inclined, you see the slots are inclined to avoid cogging at the starting. Generally the slots in the rotor will be made inclined to avoid the cogging. Cogging is a magnetic locking, right. So, to avoid that we will be using this inclined slots. So, let us discuss the operation and we will move on to some questions. Okay. Mridmay Singh is asking, how can we expect the level of exam this time? Will it be same as 2019 level? It's like I have gone through the questions. It's basic fundamental questions only they are asking. Principles, operation, some constructional details they are asking. So, with respect to machines I am saying. So, it will be not much stuff. Very few questions are application oriented and little bit out of range, but not some questions falls in gate and ESE category, but otherwise it is more than 80% of paper is going to be very easy questions or very normal questions, I can say, basic concept oriented questions only. So, do not worry, if it is easy it will be easy for everyone, if it is tough it will be tough for everyone. So, do not worry. Okay. Right. So, we will have a look at the operation of induction machine. So, as I said, as I have shown stator and rotor, the major parts of any rotating machine is going to be two parts, stator and rotor. Stator is a stationary device, rotor is a rotating device. Okay. Induction motor stator is of generally any motor or any generator, stator is of hollow construction, because you need to insert a rotor, otherwise it is not possible, right. So, it is a hollow cylindrical construction and rotor is going to be solid cylindrical, it looks like solid cylindrical, but you can make it laminations, you can make it thin sheets in order to reduce the what I can say, to reduce eddy current losses. Okay. So, let us not get into that. I just wanted to concentrate only on operation, because I have many questions on operation, especially slip, synchronous speed and all those things. So, I am taking a stator. The stator core is again same as like an the transformer core. It is going to be made with the magnetic material. The magnetic material is of generally silicon steel. If you want to increase the permeability, you can go ahead with the cold rolled grain oriented steel, but here it is going to be CRNO, cold rolled non oriented steel. For transformer it is cold rolled grain oriented steel, but for rotating machines, generally for rotating AC machines, generally it is CRNO steel. Anyhow, steel is going to possess high permeability, low reluctance. Okay. So, I have a stator core like this. Now, on the core I can place some windings. I am not showing many windings, I am showing only few windings. Let me call this as R phase and Y phase, B phase. So, I wanted to take up 3-phase induction machine. So, that is the reason why I am showing 3 phases, R, Y, B. These 3 windings are displaced by 120 degrees apart from each other. Okay. These 3 windings are displaced by 120 degrees apart from each other, and the current circulating through those windings also displaced by 120 degrees timely. Okay. IR at an angle 0, IY at an angle 120 and IB at an angle 240. Okay. So, if you take up it as minus 120, you can write it as plus 120, no issues. So, whenever time displaced currents are flowing through the space displaced windings, remember these windings are displaced physically and the currents are displaced timely. So, whenever a time displaced currents are flowing through the space displaced windings, a rotating magnetic field will be produced, remember that. Okay. So, 3-phase currents flowing through the 3-phase windings will create a rotating magnetic field, and this rotating magnetic field is going to rotate at synchronous speed, or the speed of the rotating magnetic field we call it as synchronous speed, remember. speed of the rotating magnetic field is called as synchronous speed. It is better to say this way. Instead of saying rotating magnetic field rotates at synchronous speed, instead of that, it is better to say the speed of rotating magnetic field is the synchronous speed. Okay. Right. Why it is rotating? Because windings are placed in circular manner. That's the reason why once the flux will, resultant flux will establish here, resultant flux will establish here, and resultant flux will establish here. That means what? It moves on, like this, it moves on like this. Why it is looking like moving? Because the windings are placed in a circular manner. If the windings are placed in horizontal manner, the resultant flux would have moved in the horizontal manner like this. If the windings are placed in vertical manner, like or inclined manner, the resultant flux would have moved in this manner. Wherever the current carrying conductor exists, there the flux exists, flux establishes. So the windings are established or windings are arranged in circular manner. That's the reason the flux is establishing in circular manner, and hence we are calling it as rotating magnetic field. Basically, magnetic field won't rotate, it will establish. As the windings are arranged in circular manner, it is looking like rotating magnetic field. This won't happen in the transformer because the windings are not arranged in the circular manner. Rotating magnetic field is absent in the transformer because the windings are not arranged in circular manner. They are arranged in horizontally on one core on each and every limb or legs. Okay. So anyhow, so this rotating magnetic field is absent in the transformer. Remember that point. Now the rotating magnetic field is going to link with the stator and induces an EMF in the stator. The EMF equation is same as the transformer equation. Now, in the hollow part, we will be placing the rotor, right. This rotor can be squirrel cage type or slip ring type. I am taking only squirrel cage. Generally, the squirrel cage rotor doesn't have any phases, doesn't have any winding displacement. It is basically generally a rotor bars composed with rotor bars, okay, and they are short circuited on both the ends, on the front end and rear end. The windings are short circuited. Okay, it is just a rotor bar conductors, I can say. Now the rotating magnetic field is the magnetic field is rotating. Therefore, there is a relative speed between stator winding and rotor winding also. No, magnetic field is rotating, stator conductor is stationary, so EMF is inducing. Magnetic field is rotating, here rotor conductor is also stationary, EMF will definitely induce. Wherever there is a relative motion between conductor and magnetic field, definitely there will be an EMF induction. That is what dynamically induced EMF. Okay. So here, so EMF is going to be induced in this rotor conductors. Now EMF wants to oppose the very cause of its production to satisfy the Lenz's law. So the EMF induced is because of what? Magnetic field. So how can it oppose the magnetic field? EMF is an electric quantity, magnetic field is a magnetic quantity. So EMF is going to drive a current in the short circuit conductors and it is going to set up a flux phi2. Now this flux is trying to interact with the stator magnetic field or this rotating magnetic field. Let me call it as phi1. So the phi2 is going to be established from the rotor side. Now the phi2 is trying to interact with the stator flux. Why? In order to satisfy the Lenz's law. While the phi2 is trying to interact with the phi1, because of that interaction, a force will be created on a moving body. Stator is not a moving body, rotor is a moving body. So because of the interaction, a force will be created. Now you can observe that force on the rotor conductors. Okay. Why I am taking force in the clockwise direction only? Because let us assume the rotating magnetic field is, the magnetic field, stator magnetic field is revolving in the clockwise direction. It is like my hand, right hand, it is moving from like this or left to right like this. Okay. So on top of my head it is moving. So it is hitting my head and moving like this. It is hitting my head and moving like this. So I will get a pain, right? If I get a pain, I should go and stop that. Should I go like this? Will I go like this? No, right? We should not go in that manner. If somebody is hitting me and running in that direction, I should also go and run in that direction. I have to catch him and I have to hit him. The same way here also, if the flux is hitting the rotor and going away, because of hitting action EMF is inducing, that EMF has to counter the very cause of its production or oppose the very cause of its production. So in that, because of that, this flux is going to interact and create a force, and the force will move the rotor in the direction of the very cause of its production. Okay. So the force tries to move the rotor in the direction of RMF or stator magnetic field. So that is how the rotor gets started. Slowly it starts from 0, 10 RPM, 100 RPM, and slowly it increases. Okay. While running, the rotor speed is going to be increases. Okay. Now if the rotor speed increases, what will happen? The relative speed is going to be decreases. If the relative speed decreases, the EMFs induced in the rotor are also going to be decreases. That's a different story. But what I wanted to say is here, between the rotating magnetic field and rotor, there will be a difference in speed right from starting to till the end. There will be a difference in speed. The difference in speed we call it as slip speed. The difference in speed we call it as slip speed, ns minus nr. It is an RPM only, slip speed I am writing. Per unit slip is written as ns minus nr. Ns is nothing but synchronous speed of the rotating magnetic field. Nr is nothing but rotor speed. The difference in speed divided by synchronous speed, you can call it as per unit slip, because it is an actual speed. Slip speed you can also call it as, or difference in speed. Okay. Slip speed or relative speed you can also call it as. So relative speed with respect to its like actual value by base value. That's the reason why I am calling it as a per unit value. So per unit slip. Okay, remember this. We represent this with S. So if you solve this one, the rotor speed can be written as Nr is equals to Ns of 1 minus S. This is very, very important formula. And of course the slip speed, and of course this one also. Okay, this is one important formula. And remember the principle of operation. You see you are giving a supply, it is producing a flux, and the flux is linking with the rotor. On the rotor you are going to keep a mechanical load. So the mechanical load is driven by what? The force, but force is because of what? Induced EMF. So the reason behind the production of mechanical energy is EMF. Okay. So principle of operation, don't say that it is an Ampere's law. Of course the force is induced because of interaction of fluxes or current carrying conductor only, but still we call the principle of operation as mutual induction, because EMF is the main reason for the production of force here. EMF is induced first, force is induced next. That's the reason why the principle of operation, mutual induction principle. Okay, right. Okay. Now I wanted to tell you one more point here. I have taken the EMF equation, right. Let me put the induced EMF on the rotor side, 4.44 into F into, this is rotor frequency, and the resultant flux, anyhow I am writing it as resultant flux, and the number of turns on the rotor side N2, some winding factor, it will be like this. So the induced EMF is proportional to the frequency of induced EMF. Generally we write frequency of induced EMF like this, Pn by 120. It is not P into Ns by 120, it is actually Pn by 120. This N is relative speed. This N is relative speed or slip speed. So you can write it as Ns minus Nr divided by 120. That means the frequency of induced EMF depends upon relative speed. It is like this. Some flux is going on my head and hitting my head and going away, hitting my head and going away. at what speed, at how much different speed it is going and hitting. If my hand is this much distance away from my cheek, if you hit hard, I will get a pain, huge amount of pain. This much distance, hit like this, you will get a less pain. So, if the distance is more and hitting more, if you are hitting, you will get more pain. Are you getting me or not? Okay. Like that the pain will be there. So, if the relative speed is more, frequency of induced EMF is also going to be more, right. So, if the relative speed is less, frequency of induced EMF is also going to be less. Now, in the rotor, what is going to happen? Right from the beginning to ending, the speed is changing 0 to near to synchronous speed. So, if the speed is changing, what will happen? If the speed is changing, what will happen? As the rotor speed increases, this difference decreases. If the difference decreases, I can say that the frequency of induced EMF in the rotor also decreases. So, here F2 is a function of what? Relative speed. We also take up this as, if you multiply and divide with ns, P into ns by 120 into ns minus nr divided by ns. So, we take up this as slip, na? And what about this? Generally, it is related to synchronous frequency, we write it as with supply frequency. So, this is my rotor frequency. This is the rotor frequency induced in the induction motor rotor while running, okay, right. So, that these 2 points are very, very important, and based on that you will get a question. Let us have a question, let us look at the questions. The operation of an induction motor is based on, is it based on Lenz's law, is it based on Ampere's law, is it based on principle of mutual induction, is it based on self induction? Do not go with Ampere's law, this is the principle of DC motor. Except for DC motor, remaining all electrical machines, okay, the operating principle is going to be electromagnetic induction only, okay. Electromagnetic induction is the principle of operation except for DC motor. Look at this one. Rotating magnetic field is produced in a single phase induction motor, 3-phase induction motor, DC series motor and AC series motor. Okay. Rotating magnetic field is possible. If you want to get a rotating magnetic field, 3 windings must be arranged in circular manner or 120 degrees manner, and they should carry 3-phase currents, which is not available in single phase winding, single phase induction motor. So, you cannot expect rotating magnetic field in single phase induction machine, okay. Anyhow, when it comes to DC series motor also not possible, AC series motor also not possible. So, the best possible answer is what? 3-phase induction motor. Now, look at this one. The starting torque of a single phase induction motor is, okay. If you do not have a rotating magnetic field, that means if you do not have a rotating magnetic field, what I can say, in the 3-phase induction motor we have a rotating magnetic field that is linking with the rotor, creating a counter flux, and therefore they are interacting and creating a torque. So, there is a production of torque, there is a force production and which can move the rotor. When it comes to single phase induction motor, rotating magnetic field is absent, okay, right. So, you do not expect a torque or you do not expect a a force, or even the force is produced because of forward flux lines and backward flux lines, the net force production on the rotating body is going to be 0, okay. So, that is the reason why the starting torque we call the starting torque in a single phase induction motor will be 0, okay. That is the reason why we call single phase induction motor as a non self starting motor, whereas a 3-phase induction motor as a self starting motor. 3-phase induction motor is a self starting motor, single phase induction motor will be a non self starting motor. And remember, in single phase induction machines, shaded pole induction motor is self starting, remember that point. Let us have one more question. The difference between synchronous speed and actual speed is nothing but rotor speed. Synchronous speed, how will you represent? ns, okay. So, the difference is going to be ns minus nr you call it as slip speed. You call it as slip speed. Okay. Now look at this one. The value of slip of an induction motor at synchronous speed. The value of slip of an induction motor at synchronous speed. Slip is equals to ns minus nr divided by ns. So he is asking slip at synchronous speed. That means what? Nr must be equals to what? Ns or not? So the numerator will be 0. So your slip will be 0 or not? So rotor is catching the rotating magnetic field speed. So when the rotor catches the rotating magnetic field speed, there is no relative speed, or slip speed is going to be 0. Now look at this one. A 5 kilowatt 50 Hz 6 pole slip ring induction motor runs at 960 RPM. Calculate its synchronous speed, ns, and percentage slip. Okay. So what is the synchronous speed? It is the speed of rotating magnetic field. Generally it is given as 120 into F by P. Okay. What is asking? Synchronous speed and percentage slip. 120 into frequency, how much he has given? 50, divided by number of poles 6. 12 5s are 60, so 6000 divided by 6. You will get 1000 RPM. So 1000 RPM, this is the only option, and you can find D. And if you want to find out slip also, percentage slip will be ns minus nr divided by ns. So you will get 40 by 1000 or 4%. Okay. Right. If you look at the next question, the synchronous speed of a 3-phase induction motor having 20 poles and is connected to 50 Hz source. He is asking synchronous speed. Ns is equals to what? 120 into 50 or 120 into F divided by poles. Poles are 20. Numerator value is 6000 na. So how much you are going to get? 300 RPM or not? Alright. So these are the questions which were asked in RRB. So let's have a look at one more question. The number of poles of a 3-phase induction motor when the speed of the motor is 600 RPM. Remember, speed of the motor is 600 RPM and supply frequency is 50 Hz. He is asking number of poles. He is asking number of poles. So if you take up the formula, this one, ns is equals to 120 into F by P. So P is equals to 120, frequency he has given 50, and poles he is asking. Ns if you substitute as 600, numerator is 6000, denominator is 600, you will get 10. Option A is readily available, but I feel this is wrong, because you are substituting synchronous speed. You are substituting synchronous speed as what? 600, but this is not a synchronous speed, na. It is a speed of a motor. Speed of a motor is nothing but what? Speed of a rotor, which is Nr, not Ns. Okay. So Nr is 600. Nr is 600. Ns could be what? Ns could be greater than 600. For an induction motor operation, rotor speed will never be equals to synchronous speed. Remember that. Nr always less than Ns. Rotor speed will never be equals to synchronous speed. If rotor catches the synchronous speed, there is no EMF induction at all. Because if flux and conductor both are rotating at same speed, there is no relative speed. If there is no relative speed, there is no flux linkage action. If there is no flux linkage action, there is no EMF. If there is no EMF, there is no current. If there is no current, there is no flux in the rotor, and hence no torque at all. So torque production fails. At Nr equal to Ns, induction motor or induction operation fails. Rotor speed must be always less than the synchronous speed. Remember this point. So don't substitute 600 here. Okay. So what could be the possible answer? Okay. You see, Ns is equals to 120 into F by P. 120 into 50. poles we do not know. Numerator value is 6000. Okay. Now, if I take up 2 poles, 3000. If I take up 4 poles, 1500. If I take up 8 poles, 750. If I take up 8 poles, the synchronous speed is 750. If I take up 4 poles, 1500. If the synchronous speed is 1500, rotor speed is 600, very long, na? Very huge difference, no? So, in that huge difference, the motor will not operate. Induction motor operation very near to synchronous speed. Induction motor operation is very near to synchronous speed. So, 4 poles could not be the correct answer. If you take up 6 poles, 1000. If you take up 6 poles, 1000 RPM for 6 poles. 6000 divided by 6, you get 1000. 1000 is also far away. Okay. If you take up 8 poles, 750 RPM you are getting. 750 RPM, the 600 RPM is near to 750 RPM. Na? So, I can say this could be the possible answer. Number of poles can be 8. Okay. 20 is a larger number. You know, if you go ahead with the 5 is an odd number, don't select this one. Poles must be even. Okay. So, the best possible answer is 8 rather than 10. Now, look at this one. Slip rings for an induction motor are made up of. Slip rings, they are not brushes. Okay. On the rotor, you can have slip rings like this. 3 phase windings. Okay. On this, you can have brushes. Okay. The slip rings are always in contact with the brushes. So, slip ring should be free from wear and tear and production of heat, because they are rotating now, always in touch with the brushes. So, you'll get lot of amount of heat. So, to avoid or to protect from the temperature and all those things, generally it is made from phosphor bronze. The same material is used for designing springs also, because it will not allow the change in resistance. Even though it is carrying the current, the temperature production is going to be very even though there is a temperature production, there is no much change in the resistance, because the material will be having low temperature coefficient. This material will be having low alpha naught. The temperature coefficient is going to be very low, so that resistance will not change, right. So, because of that reason and some good conductivity, okay, we can generally use phosphor bronze. Which of the following is not a part of squirrel cage 3-phase induction motor rotor? Okay. Which of the following is not a part of squirrel cage 3-phase induction motor? Okay. In motor, rotors must be there, stator also must be there, shaft also must be there. Carbon brushes. You see, carbon brushes. Why? Because squirrel cage rotor is a short circuit rotor, na? If it is a short circuit rotor, rotor conductors are not brought outside like in the slip ring rotor. If the conductors are brought outside, slip rings are needed and brushes are needed. If you don't have any conductors outside, then what is the requirement of these brushes? Okay. So, this is the correct answer. This is not a part of the motor. For a slip S and supply frequency F, the frequency of current in the rotor will be. Okay. So, we have seen now E induced EMF equation, E2 is equals to some E2 is proportional to F2. This frequency is depending upon what? Slip, na? Slip. So, F2 is what? F2, frequency of induced EMF in the rotor, is equals to slip times the supply frequency. Okay. This is actually SF, slip times the supply frequency. Why? This is the reason why we say induction motor is a variable frequency device. F2 is very low, 1 Hz to 4 Hz. Supply frequency is 50 Hz. Rotor frequency is what? Stator frequency is 50 Hz. Rotor frequency is what? Very low. That's the reason why we call induction machine as, or induction motor as, variable frequency machine, whereas transformer is a constant frequency machine. Okay. So, these are some questions from transformers and induction machines. I hope the concepts and questions were clear. If you have any doubts, you can reach out to me, or you can post the comments in the comment box so that I can reply to your questions. We have a sale option on this SSC and RRB JE courses and all state government courses. There is a 30% sale is going on, so 30% discount is going on. Use this code SES30 and this is applicable up to 9th. Okay, right. Thank you so much.